Hello everyone, my name is Devashish and today I am going to talk about mechanical metallurgy of bulk mechanical alloying. Following is the outline of today's presentation. I will be discussing about what BMA is and how does a generic BMA's process flow look like. Then I will be moving on to explain benefits of BMA. Thereafter that I have two case studies lined up to dig deeper into the metallurgy behind current BMA processes prevalent in the industry. Finally, I will be summarizing all the learnings and then I will show you my references for this presentation. So, what is BMA? It is a process of alloying materials by severely deforming them under heavy stress. The process consists of following four steps. Step 1. Materials are placed between upper punch and lower punch in the die. Step 2. The upper punch exerts high stress on materials, and these materials are then squeezed into cavities with different diameters, which makes the material undergo various compressive, expansive, and plastic phases. So this gives rise to shear bands. Step 3. The stacked layer of materials then penetrate each other through the above mentioned shear bands. Step 4. This gives rise to alloys with amorphized nanocrystalline interface regions. So now let us take a look at the process flow of BMA. So during BMA process, as discussed in previous slide, the starting constituents are poured or placed in the die. Next, the material undergoes compaction, extrusion, and ejection with withdrawal phases in between each of the three above mentioned phases. Figure 3 shows a typical stress loading curve on the material placed in the die. This cyclical loading leads to plastic deformation of the material. In this way, a dense powder or material is obtained. But as we know that due to any type of cold working, the nature of the material changes, hence metallurgical behavior needs to be analyzed. But first, let us see why BMA is important for industry. Following are the advantages of BMA process. 90 to 95% conversion of starting constituent takes place to alloys through BMA process. The benefit of being able to replicate efficiency and the physical properties obtained in the laboratory to the manufacturing environment is another plus point of BMA. This process enables us to synthesize non-equilibrium saturated solid solutions, metastable phases, and amorphous phases by repeating the processes of forging, welding, and grinding of mixed metal powders. With BMA, we have lower processing times for formation of magnesium and magnesium-based alloys, which play an important role in construction of rechargeable hydrogen storage materials. It is also an innovative approach to make nanostructure and intermetallic compounds due to lower contamination risk and simple handling. Also during BMA process, the constituent comes in contact with only the inner wall of the die and upper and lower punches, and thus the loss of constituent is efficiently low. Fun fact, did you also know that Mg2CO cannot be formed conventionally due to high melting point of CO? Why is it important, did you say? Because Mg2CO is the main constituent of hydrogen storage tanks. So, the cost of Mg2CO production directly affects the storage tank cost. Hence, BMA has a big potential to bring down hydrogen tank costs. So, with this in mind, let us proceed with our metallurgical research on BMA. As I have said before, BMA takes place under stress. So a lot of microstructural changes happen during BMA. A lot of researchers have studied stress-strain curves for alloys made with different BMA processes and have plotted their relationships. I will talk about the metallurgical theories behind the behavior of alloys shown in those curves. I have picked up two of the most prevalent alloy formation through BMA in our current industry, and I am summarizing the metallurgical research behind them. So let us take a look at some of the case studies. So this slide demonstrates case 1, which is aluminium, iron and zirconium alloy formation. In this case, BMA was done with P6 planetary ball mill in a hardened stainless steel container with both 99.99% pure iron and aluminium, and then the samples were vacuum sintered. Firstly, only aluminium iron alloy sample were created, and then for further understanding of metallurgy behind BMA, zirconium powder was added in the ball mill. So now let us take a look at the metallurgical properties of the samples which were created through this process. So this slide shows stress strain curve of aluminium 1 Fe.3Zr alloy samples with varying milling times. The most important observations from this particular graph are the variation between the grain size is from 52 nanometer at 60 hour mill time to 45 nanometer after 90 hour milling time, and finally it becomes 50 nanometer at 100 hour milling time. Another thing to note is that the yield strength of elastic zone increased with the mill time up to 90 hour, but thereafter that there was a decrease in strength at 100 hour. Metallurgically speaking, the alloy followed trend of Hall-Petch relationship. As seen from equation 1, stress increases with decrease in diameter. With samples milled between 60 R to 90 R, the particle size is seen to be decreasing. Stress increased as indicated by purple arrow. When milling time was increased to 100 R, the particle size rose again, and that is why the stress reduced. So let us see next trial. Continuing with the results, figure 5C shows stress strain curve with varying Zr concentration in the alloy. Following were some of the observations for this trial. This time concentration of Zr in the alloy solution was gradually increased from 0 to 1%. From the stress strain curve, we can see that the stress required increased with increasing Zr concentration. The increase only lasted till 0.5 Zr, and then at 1 Zr, stress dropped by approximately 200 megapascal. On doing X-ray diffraction, it showed that Zr existed as intermetallic particles in solid solution of aluminium and iron alloy. Considering Zr as hard obstacle, shearing stress then is dependent upon the interparticle distance of Zr as shown by relation 2. Now as the Zr content increases, shearing stress increases as L becomes small till 0.5 Zr concentration is achieved. After that, further addition resulted in the coarseness of particle, and thus shear stress decreased as the limit of minimum L was achieved. This time, the sintering temperature was varied and samples were prepared. Figure 5D shows stress versus strain curve with varying temperature of sintering for aluminium 1 Fe.5Zr samples. The sample at 480 degrees Celsius showed yield strength of 854 megapascal. The sample centered at 420 degrees Celsius showed strength of 920 megapascal, but the highest yield strength was shown by sample at 400 degrees Celsius, which is approximately 1040 megapascal. The reason behind the decrease in yield strength with temperature can be increase in diffusion of Zr present in intermetallics, which increases distance between Zr particles. Again, by applying equation 2, we can see that increase in temperature, stress will decrease, which leads to decrease in yield strength. Now let us do a microstructural review to understand a bit further. From the point of view of microstructure, following are the important observations. The high strength obtained with Al1Fe.5Zr alloy results from the fine-grained structure and the dispersion of the intermetallic phases such as Al6Fe and Al3Zr. For the alloys sintered at 480 degrees Celsius for all forms of Al1FeXZr, the stress increased with the increase in Zr content to 0.5% as it refined the precipitate distribution in the alloy. Further, Zr increase on the other hand resulted in coarsening of microstructure, which reduced stress. For alloy of Al1Fe.5Zr, reduction of sintering temperature from 400 degrees Celsius to 420 degrees Celsius gave a fine and uniform distribution of intermetallic particles as opposed to the sample processed at 480 degrees Celsius. Thus, lower temperatures resulted in samples with higher yield strengths. Now, let us take a look at case 2. So, the next case is about BMA of copper silver alloy through accumulative roll bonding process. The samples were then tested in Vickers hardness test, and SEM and TEM analysis was done to understand the microstructural changes. Thus, let us review the microstructural findings first in this particular case. Working from SEM results, we have following observations. Eutectic lamella structure elongated in rolling direction after first rolling. There was no significant change in interlaminar spacing of the copper and silver eutectic lamella after second rolling cycle. After 2 cycles, local shear bands started to appear. After 5 cycles, the shear bonds became weaker, and this in turn concluded that it is the propagation of shear bonds that result in deformation of the material. Furthermore, from TEM observations, we have following. Initially, the microstructure showed fine lamella with 30 nanometer thickness and 50 to 80 nanometer thick AG lamella. After one cycle, the copper and AG interlamellar distance decreased. After 2 cycles, local shear bands started to appear. During closed inspection, selected area electron diffraction patterns showed ring patterns exhibiting the feature of a 1-1-1 texture perpendicular to the rolling direction. After 3 cycles as shown in figure 9c, lamella bent due to emergence of the shear bands, and in figure 9d after 5 cycles, 2 shear bends were distinctly visible. Now let us see Vickers hardness test result data. Now let us see Vickers hardness test results. Figure 11 shows us the hardness curve. As seen from the curve, hardness do not change much during 2 to 5 cycles, and after 5 cycles, there is a linear change till 9 cycles. During first 5 cycles in the uniformly deformed region, The local lamellar structure is still retained even with the localized shear strain. The interlamellar spacing of the copper and Ag lamella remains same for the first 5 cycles. This keeps the hardness level same. As noticed in figure 12 part E, the size of ZR nodes is not uniform until number of cycles is less than 5. Also, the nodes become uniform after 5 cycles. As seen from figure 12 F to J, the ZR node becomes more homogeneous, which increases the hardness during 6 to 10 cycles. So now let us take a look at metallurgical analysis of this trial. Based on the results we found in the previous slide, we can work on understanding the metallurgy behind the Vickers hardness curve. Let us review figure 13 as it shows that the alloy is being cold worked and therefore is undergoing recrystallization. We can clearly see the formation of nuclei taking place, and also the presence of shear bands mean that the grain growth is also starting to occur. So analyzing the hardness curve from cycle 1 again, we can say that the material is in recovery phase, but after the second rolling cycle, the recrystallization starts. Hence, there is no significant change in the hardness until the recrystallization phase finishes. So once that happens, the hardness increases gradually due to the formation of smaller grains in preferred orientation with each rolling cycle. So now with that in mind, let us summarize the learnings from the two case studies that we have covered in this presentation. So from the two case studies in this presentation, I was able to have these three learnings. Depending upon type of PMA process, multiple strengthening metallurgy take part in increasing the yield strength of the material. Alloys can be tailor-made by using PMA as per desired levels of hardness, ductility, and strength. The BMA processing presents some benefit compared to conventional alloying techniques like no contaminations, easy handling, higher extraction ratio, and faster processing time. On the other hand, I was able to identify these three challenges. The benefits in material strength through BMA are limited when the particle size falls below a specific value. Even with BMA, 100% alloying does not take place. Still, 5 to 10% constituents are present in mixture. Because sometimes in BMA we are dealing with powders, although the oxidation level is least as compared to the other processes, but it is still present. This will affect the quality of final alloy obtained. This is because of increase in the surface area of contact with atmosphere when we are dealing with powdered states. So next I'll be discussing my references which I used for making this presentation. So this slide and the next slide, the list of all the references which have been used in making this presentation. And thank you very much for your time and attention.